Alright, welcome back everybody. In this video we are going to be talking about information from section 10.7 of AP Calculus BC, the alternating series test for convergence. Alright, so basically up to this point we've been looking strictly at positive series, series that have positive terms. Starting today we're going to start looking at, alternating series, things like 1 minus 1/2 plus 1/4 minus 1/8, etc., where the terms alternate back and forth from positive to negative or negative to positive. That's what makes them alternating series. So it's important for us to be able to recognize that something is an alternating series, and this isn't terribly difficult. What you see in this box are the three most common forms that we'll have for alternating series. You might see something like this, something like these. In all of these forms, the even numbered terms are positive and the odd numbered terms are negative, because what we have here is we have this alternator piece. And when we talk about alternating series, we're usually operating under the assumption that this a sub n is strictly positive. We can also have alternating series where a sub n is strictly negative, but in this box, everything assumes that a sub n is a strictly positive series, that we've boiled the negative from any a sub n terms into the alternator. So now if you look at this, as we cycle through the values of our summation, these are all going to end up being, if I look at this one, -1 to the n, starting at 0. Well, when this exponent is 0, -1 to the 0 is +1. And then when I go to n is 1, it's -1. And when I go to 2, it's +1. And so what I see in every one of these forms, and here we start at 1, -1 to the second is +1. -1 to the 2 plus 1 is -1. And so we've got to pay attention to the index where the summation starts and what our exponents are in these alternating terms. But every one of these forms, we start with an even numbered term, and all the even numbered terms are positive and the odd numbered terms are negative. In all of these forms, if you look at how it cycles through with the alternator, all the odd numbered terms are positive and the even numbered terms are negative. And this third one is not necessarily obvious to people that it's an alternating series, but you have to consider what's going on here. When we have the cosine of n pi as an alternator, imagine this one, for instance. That first one is cosine of 0 pi, and we know that cosine of 0 is 1. When I put n equals 1 in here, it's cosine of pi, and we know that the cosine of pi is -1, because it's on the opposite side of the unit circle. And as we cycle through these coefficients for pi, the cosine of that quantity just flops back and forth from one side of the unit circle to the other, from +1 to -1. And so this is another alternator that you might see in a series. Just recognize that in essence, this means the same thing as, -1 to the n. All right, let's get down to business then. The alternating series test assumes that the a sub n portion is greater than 0. And then these alternating series, the sum from 1 to infinity, and any of the forms that we just looked at, converge if the following two conditions are met. Condition number 1, the limit as n goes to infinity of the a sub n portion of the summation is 0. Okay, so we need the non-alternating portion of our summation to approach 0. And then the second thing is that we reach some point where a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to some whole number. Doesn't necessarily have to be that way in the beginning, as long as at some point in time, say 5 or 6 or whatever, we get to this point where from that point forward, the next term is always smaller than the term that precedes it. As long as we meet these two conditions, the alternating series will converge. If we fail to meet one of those two conditions, then the alternating series will diverge. All right? This is actually a pretty straightforward rule to apply. Let's take a look at it. We'll look at example 1. First thing we want to do is identify our a sub n. So we're going to take out the alternating portion of this. And when we take out the alternating portion, what's left of the summation here is 1 over n. And so now we need to consider what happens, what's the limit as n goes to infinity of a sub n. If you think about this, the limit as n goes to infinity of this, denominator grows infinitely large. This approaches 0, so it's met the first condition. Second condition, we need to show that a sub n is greater than or equal to a sub n plus 1 for some value of n. In this case, that value of n is 1. As long as n is bigger than 1, a sub n is greater than or equal to a sub n plus 1. 1/2 is bigger than 1/3. 1/3 is bigger than 1/4. 1/1000th is bigger than 1/1001th. So it meets that condition. Therefore, by the alternating series test, this alternating series converges. And we're done with our first example. Okay, let's take a look at the next one. First, there's my alternator, and identify my a sub n. A sub n is equal to n squared over n squared plus 5. And so, first thing, I want to check the first condition. I find the limit as n goes to infinity of n squared over n squared plus 5. Ooh, this limit is not 0. This is 1, which is not 0. So, by the alternating series test, this summation diverges because it didn't meet one of the two conditions that it's got to meet to be convergent. All right, next, part C. Again, here's my alternating portion. So we're looking at everything else as our a sub n. A sub n is equal to square root of n over n plus 4. All right, limit as n goes to infinity of a sub n. This does indeed approach 0. So we've taken care of the first characteristic. Then we've got to consider, is this statement true for some value of n? And let's think about what's going on here. And it's possible you're going to see something that's possible here that we haven't yet seen, where the terms of this series start out, and I'm just going to generate a little table here, starting at 0. Oops. I forgot to save my setting changes. There we go. If you look at this table, you'll see that the y values start out increasing. But then once we get greater than 4, a sub n is always bigger than a sub n plus 1. Okay, it takes up to 4 until the denominator here starts to outstrip the numerator. The numerator grows faster for values up to 4. But once we hit 4, this is true. So this statement is true for n greater than or equal to 5. Therefore, we've met both conditions of the alternating series test. So by the AST, this series converges. Okay, and then part D. we've got this as our alternator. And so we need to look at what else there is there. So we're going to be looking at a sub n equals 1 over the square root of n. And now we're going to see if this a sub n meets the characteristics. All right, limit as n goes to infinity of a sub n is equal to 0, so it meets the first characteristic. And then if we investigate, it's not hard for us to see that a sub n is greater than or equal to a sub n plus 1, because as n gets bigger, the square root of n gets bigger, which makes this fraction smaller. So this is true for n greater than or equal to, and I'm going to start at 2 since that's where my summation starts. But I notice that that is true. Therefore, by the alternating series test, the sum from 2 to infinity of cosine of n pi over the square root of n converges. And that's the alternating series test and how we're going to use it. All right, you're going to want to practice and get that, get the concepts of that series underneath your belt. A little closing topic here. With the series that we looked at prior to this lesson, the ones that all the terms were, positive, there were only 2 possibilities for their behavior. They could converge or they could diverge. When we get into alternating series, there's actually 3 possibilities. Those series can diverge, they can converge conditionally, and they can converge absolutely. So when we use the alternating series test, it sorts it into these 2 groups. It sorts it into diverges, and that it's going to be one of these 2. But we're not ready yet to talk about the difference between converging conditionally and converging absolutely. That's a topic for another lesson. But just know that that's coming. At some point in time, we're going to talk about alternating series and what happens and the difference between conditional and absolute convergence. But not today. All right, that takes us to the end of our video and the end of section 10.7. We're going to come back next time and get into section 10.8. Which is the ratio test, probably my favorite of all the convergence tests, coming up next. All right, we'll see you then. Have a great rest of your day, everybody, and for now, bye-bye.